right. So yeah, with the binary search, I think this is where we left off, right? Looking at this code. What does it do? Oh, here, I think I have to refresh it. Yeah, okay. Contains, just calls this private binary search. It checks if the current exists or not. If it doesn't, well, it's not there. Then I do this comparison. This is a binary search tree. So the elements in this tree must be comparable in some way. They must be. Otherwise, there's no way to add them with that like orderedness property. So the elements, it's a generic thing, but the elements must at least be comparable. Otherwise, how would you add them? So because we know they're comparable, we know we can call this compare to method. So I get the data from the current, and I compare it to the element I'm looking for. And this was just saved into a comparison variable because it made the code a little cleaner, I think. But the value in that comparison variable is either going to be negative, 0, or positive. If it's 0, it means they're equal. Okay? So that's why that first check, if comparison is 0, return current, because return current is the node containing the element you're looking for. So this binary search, be aware that this binary search returns a node. But the contains, the public one, just checks if it returns something that wasn't null. So if comparison is 0, we found it. Otherwise, depending on the positive or negativeness of the comparison variable, I either need to look to the left or to the right. But the big point here is, at most, one recursive call could happen. Where the other implementation, the other search that we looked at, the naive one, and I call it naive, it's not a bad one, it's just that there's no, we couldn't take advantage of those details we knew about the data. So because of that, we didn't know if it was in the left or the right subtree. And because of it, we may need to do a recursive call to contains for the left subtree and the right subtree. So this one might have 2 recursive calls. But the binary search one, pardon me, will only ever have 1. And that's important. So this was kind of, we talked a little bit about how it went. Okay. Binary search tree operations. Okay, so what are the methods we would want? So if we're writing an interface, what do we want to be in the interface for a binary search tree? Well, we get everything we need to know. We get everything we need from a binary tree, but what else? Well, add. We remember add would have to be special for a binary search tree versus a more general binary tree because add has to be added in a certain way. So imagine, add is basically going to be a binary search. But we had a rule. We're allowing duplicates in our tree, and if the value is a duplicate, it goes to the right subtree. That was the rule. We could have defined it where duplicate values go to the left, but we're doing to the right. So here's like the pseudocode for an add. I mean, the idea is do binary search for where you would expect that element to be. So if I'm looking at a tree, do I have an example of a tree in a moment? Here, I'm adding 13. If 13 existed in this tree, where would it be? That's where I want it to go. So look for 13. Okay, is 14, where would 13 be relative to it? Well, the left subtree. 8 must be in the right subtree of that. 12 must be in the right subtree of that. Oh, there's nothing there. Let's say that 12, the right subtree referenced null. Great. That's where I'm going to put 13. Fantastic. Just put it there. Done. Added. So if the node does not exist, insert the node there with the element to be added. If the node does exist, if the element is less than the current node, call add on the left subtree. If it's greater than, call it on the right subtree. It'll be recursive, but that's the trick. Now, where it could get funny is imagine I wanted to add 12. imagine 13 was already added, and I wanted to add 12. It's still the same algorithm, but I just want to emphasize it because it might feel like it's a special case, but really when we go through the code, it ends up not really being. So the reason I'm saying 12 is 12 already exists. So what would I do? I want to add 12. Well, 12 goes to the left of 14, goes to the right of 8, and now I'm looking at 12. Remember, duplicates always go to the right. So is 12 greater than or equal to the value in the current node? Yeah, okay, go to the right. We're looking at 13. Where should 12 be relative to 13? Go to the left. Oh, it's null, add it there. So if we were to add 12 after adding 13 in this example, it would be the left child of the 13. So just be aware that duplicates might feel a little funny, but it's going to work just fine. So here's an example of adding a bunch of numbers, starting with an empty tree. If we add 26, boom, it's the root of the tree. Then we add 15, well, it must go to the left, and there's nothing there, so put it there. Add 38, must go to the right, nothing there, put it there. 31, well, must go to the right, then to the left, and so on. So this is how a tree would be built by adding the elements. And add becomes simple to use, not necessarily implement. I'm not talking about the implementation details, and the implementation details really aren't that bad at all. But it becomes really simple to use because you don't need to specify anything about the add other than the element you want to add. The decision on where it goes is handled entirely by the method itself, internally to the class. The add method must take care of deciding where to put it based on the properties of a binary search tree. So it's easy to use. I don't need to specify where I want it because there's only one place it goes. I call add, it's got to go where it would have to go. Min and remove min. This is where things get a little hairy. So finding the minimum value is easy. Where is the minimum value in a binary search tree?
Far left.
The furthest left node you can get to. Start at the root and go to the left until you can't anymore. It's the smallest. Same thing for the biggest, but you go to the right. So given the nature of binary search tree ordering, the node with the minimum element must be the leftmost node. Now, there are three cases to consider when looking for the minimum node. The leftmost node is the root. That could be the case. It could be the case that the root is the smallest element in the tree, meaning the root has no left subtree. And that's fine. It's still a binary search tree. The other case is the leftmost is a leaf node. It has no children, it's just a leaf. And then the last case is it's an internal node. It doesn't have a left subtree, but it has a right subtree. I think one of the example above has that. No. Okay, none of them do. We can make this argument for 38 being the biggest. Let's consider 38. This would be that funny case of, okay, 38's the biggest value in that tree. But it's not a leaf node, it's an internal node. This could also be true for a minimum value, but this particular example has it with the biggest value. So finding the minimum is simple. Just keep going to the left. If assuming a root node exists, keep going to the left subtree until there's no more left subtrees. And then you're at the minimum value. Remove is going to be trickier though, because imagine I was removing the maximum. Say I get rid of 38. What do I do? I'm in a bit of a pickle here, aren't I? Because 38, like look, if I'm removing 7, that's easy. You just remove 7, the minimum value. There's no consequence to the tree other than just removing 7. But if I'm removing 38, okay, we've got an issue because 38 has a child. What are we going to do with that child? You might have ideas, and maybe they're right. Okay. If I were to remove 7 from that tree, 9 would be lost. But here's what I can do is, well, in this particular example, it would be safe to put the 9 where the 7 was. Because we know 9 is less than 15. 9 is less than 15 because, well, it's on the left-hand side of the 15 tree. So we know it's safe to be the left child. So it's fine. And where else would we put the 9? We can't put the 9 anywhere else. It actually has to go there. So if we wanted to remove the minimum, we'd have to be careful about knowing, okay, I guess all we really have to do is, if it's a leaf node, whatever, otherwise, replace the node that was removed with its right subtree. And that'll always work, I guess. Remove 9, it's fine. If you remove 15, we'll replace with its right subtree. If you remove 18, it's fine. If we remove 26, replace it with the right subtree. So 26 is a funny one because it's the root node, but you're just replacing the node with its right subtree if it exists. It's possible that the right subtree might be null. It's fine. So case 1, the minimum value is the root node. This means that there's no left subtree. And the reason we know there's no left subtree in this example is because if there was, the minimum value wouldn't be the root. So there may be a right subtree. Therefore, simply replace the root with the root of the right subtree, which may be null. The ordering is preserved because nothing is to the left of the root. Everything to the right of the root is larger than the value in the root. The right subtree is a binary search tree by definition. Therefore, if the right subtree becomes a new root, we're good to go. The binary search tree's order will be maintained. It's fine. Case 2, the minimum is an interior node. This means that the node has no left subtree, otherwise it wouldn't be the minimum. A right subtree exists because it's an internal node. Therefore, replace the node with the node's right subtree's root. The node being removed parent's left child will become the node being removed right child. Which might sound like a lot of words, but really it just means I'm removing 7, the node being removed's parent, which is 15. Its left child becomes the node being removed's right child. It sounds like a lot of words, but that's all I'm saying. And then case 3, all right, by eliminating only a leaf, wait. I missed the leaf node one, but that one's true. Remove a leaf, everything's fine. Okay. And why is this guaranteed to work? Well, if I replace a node with its left or its right subtree, the reasoning is exactly the same as case 1 when it was the root. Nothing is to the left, can't be. Everything to the right must of the node to be removed is larger than the node, but it's less than the node of the parent. Therefore, oh, and it's also a binary tree. Therefore, if the right subtree replaces the node being removed, the binary tree is maintained. Now, if you actually were kind of like really thinking about this, the replacement rule is actually the same for all 3 cases. It doesn't matter. The replacement rule is remove the node and replace it with its right subtree. If I'm removing the root, I remove the root and replace it with its right subtree. If it's an interior node, you remove it and replace it with its right subtree. And then the leaf. Now this might feel like a little lame, but like if I'm removing 9, I remove it and replace it with its right subtree. But its right subtree is null, so whatever. So the algorithm, or the strategy I'm using to remove the minimum is actually the same regardless of the case. Which is kind of nice because we identified 3 unique cases we have to account for, but we only need one solution to solve all 3 cases, which is nice. Like, remember how it was funny with, like with a linked queue, right? Remember how there was that edge case of like, well, what if there's nothing in there? What if there's one thing in there? And how the adding and removing can get tricky? With this, it feels even simpler. The same rule. Remove the node and replace it with its right subtree. If its right subtree is null, that's fine. You replace it with null. And that just means it was a leaf. The exact same thing is going to be true for removing the max. It's just replace the left and the rights. If you're removing the biggest value, you remove it and replace it with its left subtree. It might be null, it might not be. It's fine if it's the root, same solution. So the algorithm for those removes are nice. Where things get tricky is if I say, remove 26. This is a general remove. So I'm not saying remove the minimum, remove the maximum. So I can specify the node I want to remove. If I said remove 7, whatever. If I said remove 34, whatever. What do I do if I said remove 26? What do? I'm going to give you a minute. Think about it. Talk amongst yourselves. See if you can come up with a strategy that could work. I will give you perhaps a hint. I don't know if this is a hint. Is when I tell you the solution, I guarantee you'll be like, oh yeah, that's brilliant. Yeah, it's so simple. It's nice. But that's only in hindsight. What? Oh, okay. All right, does anyone have any ideas? All right, I won't make you answer. Okay, I will make you answer because you put your hand up. But raise your hand if you have an idea. Couple people. Okay, what were you going to say?
It's probably wrong, but we were saying that you just make a new tree. If it's 26, don't add it.
Okay.
Like use your add function. Or add
Honestly, hey, there you go. There you go. Not a bad idea, actually. But perhaps, actually, I don't even know if my idea that I would say is nice and elegant. I like that one. There's a niceness to it. Yeah.
Would that be like n complexity for?
Yeah. So here's what we do instead. And I promise you this is going to be intuitive. And if it's not, you're thinking too hard. I want to remove 26. Everything to the left of 26 is smaller than 26. And obviously smaller than everything in 26's right subtree as well. Right? If the number is less than 26, it's going to be less than all the numbers bigger than 26. Right? All the numbers to the right of 26 are bigger than 26. Or equal to 26, I suppose. And remember, we can always find the smallest element in any tree or subtree by always going to the left. So what we do is the node we remove, we go to its right subtree, not just the right child, you go to the root of that whole subtree, which is the right child, and find the smallest node in that tree. Is that what you were saying or something? Because you looked at him like, mm-hmm. No? Oh, I thought maybe you figured it out or something. What?
Why don't you go to the left subtree and go all the way to the right?
Because we put the duplicates to the right. If we put the duplicates to the left, that's exactly what we would do. So here's why it works. If I go to the furthest left node in the right subtree, I found the smallest node in that subtree. There is no value smaller than it. Because if there was, you'd go to the left again. So you go to the right one from the node you want to remove, and then go all the way to the left. In this case, 31. This is a small example, but in this case, it's 31. 31 is the smallest value in that right subtree. This is the smallest number that exists in this binary tree. This is the smallest number bigger than or equal to the root, or the node I want to remove. I replace it with that. 31, that node, the smallest node in that right subtree, is the leftmost node in that right subtree is definitively less than everything else in that tree. But it must be greater than everything else in the left in the root's left subtree because it's in the right subtree. So you can replace that node with you can replace the node being removed with that one. And it's going to work because, well, we've established it's got to be bigger than everything in the left subtree. So that part's fine. And it needs to be smaller than everything else in the right subtree, or equal to. Well, and that's also the case because it's the leftmost node in the right subtree. Does that make sense? If I picked any other node in the right subtree, we're going to have an issue. Because it's not the smallest node in that tree, meaning if we picked a node that wasn't the smallest, then there would be a node in the right subtree that was smaller than the new root. And that would clearly violate the binary search tree rule. So that's the rule. It's intuitive. Now, if you're starting to think, how am I going to code that? You're jumping ahead. Don't overcomplicate it right now by trying to complicate the algorithm with the implementation. The solution is replace the node being removed with the node's right subtree's leftmost node. The right subtree's smallest value. Because that smallest value is guaranteed to be smaller than everything else in the tree because it's the one we picked. That's the smallest. But it must have been greater than everything in the left subtree. And like the other person brought up, it would be, we'd have to flip it if we put duplicates to the left. But we're not, so this is fine. Any questions about that? Though I will say, there's something nice about the idea of just create a new tree without 26. There's something about that that's kind of nice, isn't there? Yeah. All right, case 1. If the node being removed is a leaf, then just remove it. Yeah, great. Case 2. If the node being removed is an interior node, then things get hairy. In some cases, this may be simple. If 15 is removed, replace it with its child, right? So if 15 is removed, you replace it with that. Because there's no right subtree, it's fine. The trick is to replace the node. Oh yeah, so the trick is to replace the node with its in-order predecessor or successor. If 26 is removed, 15 is the value of the tree that comes right before 26, could replace it. But again, because we could have duplicates, we'd have an issue. Although I guess it wouldn't be an issue, would it? Because if there was a 26 over here, if I replaced it with 15, it would still work, eh? Huh. Yeah, I guess it doesn't really matter. Replace it with the in-order predecessor or successor. So what do we got here? Remove 70. That's, oh, oops. That's easy, it's a leaf node. Remove 7. All right, you replace it with its in-order successor. That's 9. Remove 38. It looks like in this particular example, I was replacing it with its in-order predecessor. So its left subtree's biggest value. So that would be the 36. Remove 26, that's the root. I replaced it with the 15, the predecessor. So in this example, I was doing with the predecessor. And yeah, it looks like it would be fine to go with the left or right, but it just feels nice to go to the right if that's where you're putting the duplicates, because it could be replaced with the same value. Yeah?
So when you're moving 26, you could go with either
Yeah.
side.
Now, I like the idea of going with, if you put the equal values to the right, go with that strategy, because then if I'm removing 26 and the tree has another 26, the root node would be replaced with the equal value 26. So, it's very stable. Doesn't really matter. Implementation-wise and definition-wise, it's fine, but it just feels a little better. But it doesn't matter. Contains, like the other data structures, a way to check if a given element exists. This is the log base 2n, it's just the binary search. Counting the number of a given element. So this is a funny one. Similar to contains, to count the number of times a given element exists with the binary search tree, binary search can be done. However, instead of returning like a true or false, as soon as the element is found, we have to do just like a tallying thing. It's 1. If I find the thing I'm looking for some element x, and I'm at a node that contains x. So how many elements are in that whole tree? Well, it's 1 plus however many over here and however many over here. But because it's a binary tree, we can only look to one side or the other, right? And because we always know duplicates go to the left, well, right? But, yeah. Cool? So at any given node, if it's the node you're looking for, or if it's the element you're looking for, add 1 to however many are over here and however many over here. If it's not what you're looking for, okay, fine. It's 0 plus however many are over here or over here, depending on, again, greater than or less than. Okay. Binary trees get their value, we exploit the property of how a binary tree, the orderedness of the data, the sortedness of the data, and the structure of the tree. But all of that advantage that we get about like a binary search being log base 2 versus linear, that all depends on the tree having a good structure. We want our binary trees to be what we call balanced. A balanced tree has the property that any node in the tree, the height of its left and right subtrees can differ by at most 1. For any node in the tree. So it's not just the root, any node in the tree. The left tree is balanced. Okay? It's balanced because there is no node in there that has a difference of height more than 1. The root and the left subtree of the root have a difference of 1, but it doesn't exceed 1, so it's still balanced. Still good enough. Best case scenario, we want it to be that half the nodes are always to the right, left and right of any given node. Half over here, half over here. That's the best case scenario. But that, we'd still call it balanced. But the tree on the right is not balanced. Sure, the right subtree of the root is balanced. It's the same height. But the root's left subtree doesn't, like, the difference is greater than 1. The height of the left subtree is 0, and the height of the right subtree is 1. Or it's 2. 2. And that's a difference greater than 1, so it's not balanced by that definition. So the balance property is important since it's the reason binary search is efficient. Imagine I gave you the numbers 3, 5, 9, 12, 18, and 20 to be added in that order. How is it going to happen? It's going to happen like this. You add 3, add 5, goes to the right. 9 goes to the right. 12 goes to the right. 18 goes to the right. 20 goes to the right. And then the GIF stops. But the point is, that does not look like a binary tree at all, does it? It looks like a linear collection. Remember, the worst case scenario when doing a binary search on a tree is you got to go all the way down to the leaf node that's as far away. And the height of a binary tree in relation, relative to like the number of nodes, has that log base 2 relationship, if it's balanced. If it's not balanced, the height of this tree is linearly related to the number of nodes in that tree. It's just a singly linked structure effectively. This is a linear collection. If I was doing a linear search and I was looking for the number 20, how many nodes do I have to look at? All of them. That's not log base 2. And it's not log base 2 because remember, when I was doing a binary search, every time I looked at a node, I eliminate, if it's not the node I'm looking for, if it's not the data I'm looking for, you eliminate that node from your search, plus everything in the left or right subtree, depending on which way we were going. If the thing we were looking for was over here, we eliminated that node, and then hopefully half of the other remaining things. We eliminate a lot of things with every check. Here, we only ever eliminate one thing every time we check, just like a linear search. Is 320? No, go to the next node. Is 520? No, go to the next node. We're only eliminating one thing every time we do a check, and that's a problem. So this is a degenerate tree, we call it. We don't like trees that look like this. They break all of the power we got from a binary search tree. And look how like benign this example is. It's not even particularly interesting. I just happen to add these elements in order. So if I gave you data that was already ordered and you put it in a binary search tree, you're going to end up with a garbage tree. That seems like a problem. Like, what's the harm of having data that's already ordered, right? So what do? Well, there's a lot of things we could do. Here we go. Oh, it doesn't say this is, I don't remember if this is complete or full. I think, let's call it full. But like imagine this node didn't exist, it would be whatever this one isn't called. So if that was full, it would be complete or vice versa, just FYI. So there's a couple ways we can address it. And the easiest way, I'd say, is, well, with what we call self-balancing trees. The two popular ones are AVL trees and red-black trees. AVL is probably more popular, but don't quote me. And what these do is every time you modify the tree, it'll balance itself out. If it notices it's getting too big one way or the other, the tree will balance itself. It'll restructure itself such that it has that property. And real quickly, AVL. Let's see if I can come up with a good example. Any good animations? No. They do these things called rotations. Ah, here we go. Watch. So we're adding things. Suddenly it's not balanced, so it rotates. We call that a rotate. Rotate again. Sometimes the rotations get a little complicated though. We have to do the left and right rotations like that, or right and left rotations. So that's, to be clear, outside the scope of this course. That would be something you cover next year. But, interesting nonetheless. That's an AVL tree. And they're nice. Any questions about that? All right. Linked binary search tree. Now it's time to actually implement one. Now I'm going to say, I'm not going to cover all of the methods in the linked binary search tree. They're available to you. You download the code and have a look all you want. All I'm going to do is cover some of the more interesting ones, for lack of a better term. And we'll talk about those ones. So I want to make a linked binary search tree class. I want it to be like a stack or a queue such that I can ask it things, right? Like we got the interfaces. I want to add things. I want to remove things. I want to get the size, check if it's empty, check if it contains stuff, count the number of elements in there, whatever. This is not a balancing tree. It's just a regular old linked binary search tree. So we're going to need, within the class, probably going to want a field to keep track of the size, right? We're probably going to want a field to keep track of somehow the container. Now we're going to use those binary nodes, those node objects that have a left and right successor, the children. And just like the linked queue or the linked stack, where we just had like a head reference variable, reference the head, and by having a reference to the head of a linked structure, we could ultimately get to every element in that linked structure. Same idea here, but instead of a reference to the head, we reference the root. Because if we have access to the root, we can access every element from within its left and right subtree. So that's what we're going to do. So here's how we're going to start. Public class linked binary search tree. It's generic. But just like that sorted bag, we have that constraint. The elements we're adding, it's generic, but they must have an ordering defined. They must be comparable. Because with the comparable class, or that interface, or with that class, we are defining the ordering with that compare to method. And it's going to implement binary search tree, which implemented a binary tree. Start with a default constructor, whatever. We can create one where it starts with, I don't know why adds there, that should be updated too. There's only one constructor, you create it, set the root to null, set the size to 0. It's an empty tree. This is the same as all the other linked structures we did. You create it, it starts empty, whatever. I've got add there too, but that's whatever. I'm going to include a static node class within the class. So this is a class defined within the linked binary search tree class. If you download the code, you'll see this inside of it. It's called a node, and that node has data left and right. Here we go. Now this is a binary tree node, thus it has left and right, and this class is contained out there. Add. So how would I write add? Now, by the way, I will take a moment to say, you'll notice that the public method doesn't have a Java doc comment above it, right? But the private one does. It's not uncommon to not have Java doc comments for private methods. It's actually typically, you don't see them a lot of times, but these ones have them for demonstration purposes. But then you're left going like, well, he didn't include the Java doc comment for the public add. But I don't have to when, if I go, so this is the actual code you can go download. Binary search tree. The add, I don't know why until it there. The interface has the comment, has that Java doc there. So when I'm overriding something from, or when I'm implementing something from the interface, I get that Java doc comment. So I don't have to write it because I'm getting it from the interface that defined it there. I'm just implementing it. So if you've ever wondered how come some of those methods don't have a comment, chances are it's because I'm just like hijacking the one I get from the interface or inherited. Just FYI. Add. So it's got a public add. It sets root to equal to add, and that add takes an element in a root, it increases size, returns true. And then we have a private add that returns a node, takes an element to be added, and another node called current. And I think, for the sake of time, we'll stop here because this might take some time to chew on. So we'll wrap up here today.